All right, last time we left off, we had just talked about MAD, mean absolute deviation, and you had created a table that looked like this. Do you remember that? And I mentioned that there's really only 2 lines in this table. You wouldn't have to create a table to do this specifically, but it works really well for the other piece that we're going to do, which is variance and then standard deviation. So to do variance, what we do is we find the mean, and then we subtract the mean from each number. So these first 2 steps right here are the same steps that we do for mean absolute deviation. So this piece is much the same as the mean absolute. The second pieces after that, 3, 4, and 5, we're going to square those pieces that we subtracted. And then we're going to sum them. We're going to add them up. So that's what we did with mean absolute deviation as well. We added some things together, but we're going to add squares together in step 4. And then in step 5, we're going to divide by however many values we had. Again, that process was like what we did with mean absolute deviation. So the only problem, or part of this process rather, that's any different is this squaring process. We're going to have a column where we square some things. And then because we squared them, if we're wanting to find the standard deviation as opposed to the variance, at the very end down here we take the square root. So we squared some things along the way, added them together, divided by the number of them, and then we take the square root at the end. So we're still finding how far things are away from one another, right? Specifically away from the mean. So taking a look at this same data set, we're going to find the variance. So the reality is that the first piece that we did here, all of this table before we added it together, is exactly what we're going to do again. So go ahead and just rewrite what you had from the previous slide that looked like this. All that remains the same. You might be asking yourself, but you're taking absolute values there. Is that okay? And the answer is yes, because I'm going to square things anyway. So when I square things, signs disappears. So I might as well take the absolute value, right? No reason to keep the negatives around. So this is steps 1 and 2. Step 1 was actually finding the mean, which we had done in an earlier part of our problem. We'd found that the mean was 19.9. And step 2, so this was step 1. Step 2 is finding this subtraction column right here, basically. So step 3 is going to be squaring all of those values from step 2. So we're going to draw another column into our table, and we're going to square each of those values. So grab a calculator if you have one nearby. What we're going to try and do is take the x minus the x bar from the previous column. You can use the absolute values or not, and then square them. So the first one, Cora.
Which decimal are we going to? The first decimal?
So when we're squaring them, we're going to actually write out the full value. So I think this one's going to give me 2. And most of them afterwards will as well. Our answer at the very end, though, Cora, we're still going to round it to 1 decimal. So, but we want to keep decimals long in the middle of doing a problem so that we don't lose accuracy when we get to the end and do our final rounding. So when I do 1.9 squared, I get 3.61. 2.1 squared is 4.41, and I have that here twice. The 2.9 squared is 8.41. The 10.1 squared is 102.01. I've got another 1.9, so I've got another 3.61. And then I have the 7.9, which is 62.41. Sorry, I'm off a little bit in how big I wrote things, but they're all there. Okay, so that's, step 3 on that list of things to do. Step 4 is to sum them all up, so we're going to add all of these together. So if I add all of these together, what do I get? Somebody grab a calculator and add for us. Good. Okay, does everybody else have that too? Yes. All right, so that's my sum. So this was step 4, was to find the sum. And then step 5, which is called variance, is what I'm finding. It actually has the notation s squared. By the way, variance is s squared. It's to take that 188.87 and divide by my number of values, which is 7. And what do I get with 1 decimal of accuracy when I divide that? What's wrong, Adelina?
If it's s squared, why do we divide?
We're not dividing the squared. This is simply the 5th step in my, oops, it's one back.
Okay. What's the
Over
s squared
here.
for?
It's just the name.
Okay.
The problem is that what we're going to do here in a minute is we're going to take the square root of it, and it's standard deviation. That's what the S is. But standard deviation is the square root of variance. So variance would have had to have been the square of standard deviation. So when we do this over here, one more step, and we want to find the standard deviation, we're going to find S. That's going to be the square root of the variance. And so the variance notation that they use is S squared, because really standard deviation is what people are usually looking for, not variance, but variance is sort of the in-between step. It's to the name that's given there. It's also S used for, it's not used for, but when I have the sample of the data, I'm using S and S squared. If I were doing a whole population's worth of data, I would actually be using sigma, which is a Greek letter, and the mean, I would not be using X bar for. I would actually be using mu. So mu is the mean for a population of data. Like if we were to say, for instance, the entire population of OBU students and we found their average height, right? That would be mu. But if we did a sample, like this classroom, it would be X bar, right? The X with the bar on the top. And the same thing happens when we're looking at standard deviation and variance. So S is standard deviation for a sample, and sigma is standard deviation for a population.
Okay, so
Yeah.
the S is for sample, is that what you said?
S is for standard deviation. S is standard deviation. That's the S that's showing up here.
Okay.
And you see the S squared showing up because of the variance and the standard deviation's relationship.
Okay, that's like the formula for like overall.
Yeah.
Not for, there wasn't the formula for step 5.
Correct.
It's like just overall,
Exactly.
this is the formula.
Right, so overall, we're at the point where the final result is 188.87 divided by 7. Yeah. What is 188.87 divided by 7? Somebody get it?
7.
What is it? 27. And we're going to write it as 27.0 because we are going to use that one level or one decimal of accuracy. I don't think it's exactly that in your calculator. Is that true? Okay, so hold tight to what it exactly is, but in the reporting the answer here, it's 27. But when I find the standard deviation over here on part C, I want to find the standard deviation of what you really actually had, which was 26 something. What was it?
9814.
9814, more stuff, right? Something. So at that point in your calculator where you've got this expression expanded out, that's when we're going to take the square root. It may or may not on this one matter. It might give you the same value if you took the square root of the 27. But depending on the decimal expansion that you have, sometimes you'll be off by a decimal point if you're not careful to keep your less decimals long in the process. So what is the square root of the 26.9814, etc.?
5.19.
5.2. Yeah, we're still going to round to 2 decimal places at the end, so it would be 5.2. Okay, so why do we care about standard deviation? It's a good question, right? Why do we care? We actually care because it's going to come into play in the next part of the questions that we're looking at, okay? So we're not going to be finding that many of these. You're probably going to find like maybe 2 in your whole homework. If I ask for one on the test, there's going to be 1 on there. It's not going to be a big component of things, but yes, Corey?
On B,
Yes,
the 27, what is that?
it's variance.
Variance. Okay.
Yes, we found the variance. So it's called S squared. That's the notation for it. Or if you just want to write the word variance or VAR, that's fine too. It doesn't bother me in the slightest. But the 27 is the variance.
Okay.
And then when we take the square root of the approximately 27, we get the standard deviation.
Gotcha. Okay.
Okay. So all of this is actually building up to what are called normal distributions. Okay. So a normal distribution is a smooth bell-shaped curve that depicts frequency values distributed symmetrically about the mean. Normal distributions typically occur with large data sets. Okay, there is no reason to expect a normal distribution if your data set is small. If you have a normal distribution, the empirical rule is what follows from that. So the empirical rule tells you how the data is spread around the mean. And you see the standard deviation showing up in the description, right? I'll draw you a picture here in a moment. I don't have space. Well, do I have space on the next slide? I have enough over there, but I'll draw it here in a minute on this one. The empirical rule actually talks about the fact that if you are one standard deviation away from the mean, either lower or higher than that, 68% of the data will fall between those values. And if you're 2 standard deviations away from the mean, you have 95% of the data. And if you're 3 standard deviations away from the mean, it's almost all of it, 99.8. So a bell-shaped curve looks something like this. I'm not expecting you to draw them perfectly. There's no reason to care. There's just not. The height, right, the location where you're seeing the peak happening here, this location, it's drawn terribly. I even told you I didn't have to draw it perfectly, right? Pretend that's it. That's terrible. That's even worse than it was before. Oh my goodness. So like I don't mean to be rude, but I'm not clinically like OCD, but I might be a little bit. It's a little bit better. If you are really OCD, I'm really sorry. That'd be terrible. Sometimes I wonder about myself. Okay, this one will work for us. We good with this? Okay, if we go out 1 standard deviation, this is our mean, it's X bar, right here. And if we go 1 standard deviation in either direction, again, not perfect, but we'll go with it. I've got like 1 standard deviation to each direction, like from here to here. What happens is that's 68% of the data. So the data itself is all distributed underneath here, right? These are all of my data values. That's what this is representing, okay? The height is representing kind of like on a bar graph frequency, how many of them are in that place, okay? So what we're doing is we're saying, okay, let's isolate then. Let's isolate between here and here. And if I were to isolate between those 2 locations and shade it in, that right there is 68% of my data. Okay, 1 standard deviation in each direction gives me 68% of my data. Now let's say I go out 2 standard deviations. So now I'm over here. I'm spread apart further. And the standard deviation is a value we found, right? Like over here, the standard deviation was 5.2. So if I were putting this onto this chart, the X bar would say 19.9 in the middle, and then I'd do 5.2 smaller than that, 5.2 bigger than that, and those would be my X locations. And then I'd do it again. I'd go out 5.2 again in either direction to get 2 standard deviations. And then I'd go out again 5.2 in each direction to get the 3rd standard deviation. So in 2 standard deviations right here, I'll draw it in, we'll go with orange. I would be from here to here. And I would shade in all of that area, which includes the green, right? It's all of this, including the green. And I would have 95% of the data. And then the last one goes out 3 standard deviations, and we get almost everything. If I go 3 standard deviations away from the mean in each direction, and I'll mark that. I'm going to draw the picture in yellow, but I won't color in yellow because then we won't, or I won't write it in yellow because then we won't be able to see it. So this one to this one, and we'll color that in yellow. It would include all of the green and all the orange, and then this extra part on the outside, all of that. And maybe I can write it in that dark of a yellow. Yeah, maybe. This is 99.8% of the data. Okay, so we go out a little bit further, we get a little bit more data. We get out a little bit further, we get a little bit more of the data. But the bulk of the data is right there in the middle. Okay, have you heard the question, or have you asked the question before, are you going to curve the grade? You heard that? This is what it means to do grading on a curve. It does not mean what you think it means. You want somebody to just add extra points, don't you? That's what you mean when you say grade on a curve. That is not what the phrase grading on the curve actually means. It means that you make some sort of a cut point. Well, you actually look at the data set. So if I were to take all the grades in a 500 person, class of college algebra, like at a large university, like an OU or something like that, I would look for the mean score. And I'd put the mean score in the middle. And then I'd calculate the standard deviation, and I would go in each direction both ways. And then I'd go out again, and then I'd go out again. And the top values, for which there would be very few, would be A's. And the next set of values would be B's, and the bulk of the people in the middle would be C's, and then I'd have my D's, and then I'd have my F's. All it is a comparison to other people. It's not a comparison to what you actually know on the material yourself. That's what grading on a curve is. Now, that may not be the best use of a normal distribution, but things are normally distributed all the time. So when you go to the store and you get a box of cereal and the box says that it has 11 ounces, does it really have 11 ounces? Well, within a certain level of accuracy that the company feels is comfortable, yeah, it does, right? But it might not be 11 ounces. It might be 10.9, or it might be 11.2. They have to use, and they do use, normal distributions to decide how far out they can go and still be comfortable with those variations in their box sizes, okay? So this normal distribution is going to be used, we're going to use it now for a few problems. As you're doing normal distribution problems, a few caveats that you need to be aware of. You're going to draw a normal distribution curve every single time, and it doesn't have to look great, okay? What does it have to show? Well, it needs to show the mean on there, and it needs to show the standard deviations that are relevant to the problem you're working with. So if you're going out 3 standard deviations, you're going to show 1 to all 3 of the standard deviations. If you're only going out 2, you don't necessarily have to go out to 3 all the way. We're going to take a look at an example. This one's talking about an average phone call. So this one says to assume a normal distribution. That's something else that's really important. If it doesn't say normal distribution, you can't assume it, right? It would not be reasonable in certain data sets for there to be normally distributed values. Y'all's tests, when I look at your tests, I have no expectation or belief that they should be normally distributed. You're a very small group of students, right? You might be all fabulous or you might be all terrible. There's no reason to think that it's going to be normally distributed like it would be in a 500-person class. Agreed? So it needs to say that it's a normal distribution for this to make sense. This one does. It says the average phone call in a certain town length lasts 8 minutes with a standard deviation of 2 minutes. So the first thing we're going to do is I'm just going to draw out with you the entire normal distribution so you can see it once at least. And then some of the time later we may not draw the whole thing out. So this value in the middle, you can draw it solid like I did or dotted like I did before, is the average. That's the mean. It's the 8-minute phone call. And then it says the standard deviation is what? 2. So we're going to go out 2 to the right and to the left. So 2 minutes more than 8 would be 10, and less than 8 would be 6. That is 1 standard deviation out. We're going to go out 2 standard deviations now. So we're going to add 2 more to it and take 2 more away. So now I'm at 4 and 12. And I'm going to go out 3 standard deviations, add 2 more, and I'm at 14 and 2. And some of you were saying a 14-minute phone call? That's not very long. And other ones of you were saying like 2 minutes on a phone? I never talk on the phone. I have children in my household. Some of them never talk on the phone. Some of them talk on the phone a lot. So this is the distribution, okay? All right, so the question that's asked, though, is how we shade our diagram. It says that we want to know the calls that lasted. In fact, I'm going to keep this to be used on the next data set. You're welcome to not draw it multiple times, but mine are on multiple screens, so I'm going to need to draw it more than once. Do I only have 2? Nope, I have 3. Okay, so over here, my 6 to 8 minute phone call, I'm going to shade in the locations from 6 to 8. So 6 to 8 would be putting me right here. Does that make sense? Okay, now that's not exactly an empirical rule value, but I can use the empirical rule to find the shaded value that I have. Any idea what I might do to find that shaded area? The percentage. Laura?
68 divided by 2,
Right, how come?
because it's 1 standard deviation, not 2.
It's because it's 1 standard deviation, but only in one direction. So I've only got half of it. So Laura's taking a look at this and saying, hey, if I went all the way out 1 standard deviation like this would be 68%, right? 1 standard deviation in each direction is 68%. But I only have half of that because the graph's symmetric. So I can simply take my 68% and half it, and I'll have a 34% of the phone calls. So I have a 34 percentage of the phone calls, none of that's sounding right. 34% of the phone calls are lasting between 6 and 8 minutes. Okay? We're gonna do the same kind of a diagram. Picture's the same starting out. But now it wants phone calls lasting less than 4. So shading wise, I'm over here. How can I figure out how many phone calls lasted less than 4 minutes? Okay, what do you see, Laura?
You would take so 2 standard deviations would be the 4 and the 12. That would cover 95%, which means before 4 and after 12 cover 5%. So before 4 would be half of 5%.
Okay, so this is the first thing that she mentioned, right? That's 95%. That's the empirical rule, correct? Okay, how much data is in the entire graph? 100%. So I've got 95% trapped. That's not the area I want. So the area that I want would be 100% minus the 95. And what that would give me is it would give me these outer edges. But I don't want all of the outer edges. I only want the left outer edge. So I would have that value, which is it's 5%, and I would divide it by 2 because I only have half of the leftover data that I need. So this is 5% divided by 2, or 2.5%. Okay, so we're always trying to look back at how I can use the data that I have, you know, the empirical rule parts itself, to find out what I need. How about phone calls lasting more than 12?
Well, that would be 2.5%.
How come?
It's the exact same as the other side.
It is. It's just the other side, right? Yeah. So this is the same 2.5%. It's the other piece that I didn't have before. So I've got another 2.5%. Okay, makes sense? All right. The next one talks about IQ scores. So the mean IQ scores for 1,500 students is normally distributed with a mean of 100 and a standard deviation of 15. So just like on the last one, the first thing I'm going to do is going to draw the picture. And we're going to actually put in all the standard deviation pieces as well because that's because I know the questions that are about to be asked, really, and they're going to involve all the pieces. So this one in the middle is my mean. It's 100. It says my standard deviation is 15, so I go out 15. So I've got 115. 15 again puts me at 130. 15 again puts me at 145. And then I go the other direction, so I'm at 85. And then I'm at 70. And then I'm at 55. Okay. The first question says between 85 and 115. Okay, so 85 to 115 would be this data right here. So I'm going to change the question just a little bit. What data, what percent of the data is between there? It's not quite the question I'm asked, but what is the percent of the data that's represented by my yellow region right now?
60.
Yeah, it's 68%, right? This is 68%, but that's not the question that it asked. What is the question it asked? How many students? I need to know the number of students that 68% represents. You can do that in a couple of ways. One way we did it was with proportions. We said 68 over 100, and it equals some value over the 1,500, right? You can do it that way. Another way that we can do it is we could take 68% as a decimal, which is 0.68, and you can multiply it by 1,500. Doesn't make any difference which of those approaches you take. You will get the same answer. What value comes out of this 68% of 1,500? 1020, and it's 1020 what, Mackenzie?
Students.
Students.
IQ between 85.
Yeah. So bare minimum we would want to write as students. There's 1,020 students that fit this category. Is that all right? Okay. Now we're going to do more than, over 145. So that's over here. That's slightly different than a question we've seen before, but it's related to it. How could I find that little bitty yellow sliver? How did I find the outer yellow slivers over here? I used some subtraction, right? This one, however, went out 2 standard deviations, and mine right now is going out how many? 3 standard deviations, right? I've gone all the way out 3 standard deviations to the 145. So if I go out 3 standard deviations, the corresponding piece that I can use actually goes from 55 all the way over to 145. So how much area is in the 3 standard deviation area? 99.8. Yeah, it's a lot of it, right? 99.8. So I need to know how much I don't have, right? Well, how did I do that before? Subtraction, 100 minus the 99.8. And I'm only doing the bottom end or the top end, like 1/2 of it, right? So I'm going to divide it by 2 again to get just that half piece that I want that's shaded in yellow and not both of the extremes. So what is 100 minus 99.8 divided by 2? 0.1, and that is a percent. 0.1% is not the same as 1%, just like $0.5 is not the same as 0.5 cents, right? We talked about that on a previous test that you had had. So 0.1% as a decimal, if you turn it into a decimal, is 0.001. So in terms of setting this up, you can either do 0.1 out of 100 and write it in percent form, and that's x over 1,500. Or you can do 0.001 as a decimal times 1,500. No matter which one you do, what do you get? 1.5. But it's 1.5 what? Students. Which either needs to be 1 or 2, right? I mean, we can't have 1.5 of a student. No cutting students in half, strongly discouraged. So we're going to just use regular rounding rules. So we're going to go ahead and round the 1.5 up to 2 and just go with it from that perspective so we don't have to decide, well, when do we round up, when do we round down? We'll just use our normal rounding rules. So this would actually be 2 students. Okay, I have one more of the normal distribution problems. Ready? Okay, this is it. So we're looking here now between 70 and 145. So we're going to go from 70 to 145. This is not a symmetric shading. Agreed? So I got to figure out what I'm going to do about that. There are several things you could do. What do you see?
You could do, because we know 145 over is 0.2%.
Okay.
We know 55 over is 0.2%. So you could add those together, get 0.4%. And then between 55 and 145 is 99.8%.
Okay, let's actually use that. That's helpful right there. So I don't know that the first 2 pieces are useful at the moment, but you're correct if you used 0.1 instead of 0.2s. Cora, what did you have as an idea?
The same thing.
Same thing. Okay. So if we take a look at going from 55 all the way over to 145, this piece, right? It's in orange right here. That's 99.8. Correct? Okay, so how can I use the 99.8 now?
Subtract 95%.
Okay, if I subtract 95%, what am I going to get? I mean, I don't mean the number, but like visually on my picture, what am I finding?
You're going to get the percentage between the second and third deviations on both sides.
Okay, so this is going to give me, I'm using lots of colors. Let's do green. It's going to give me this space and this space added together. Correct?
Yep.
If I subtract those two. Is it all I want to do is subtract those two?
No,
What else am I want to do, Laura?
I'm gonna divide by 2,
And why would I want to do that?
because you need only one side, not both.
Yep. I can get the missing piece over here if I do it from that perspective. So if I've got 99.8 minus 95 divided by 2, I find the green piece. What is the percentage in this green piece? This isn't how I have it done on my paper, so now I'm going to have to let you guys tell me. 99.8 minus 95 divided by 2. What is it? 2.4. Okay, so this is 2.4. Now what am I going to do with the 2.4% in the green?
Add it to the 95%.
Okay, so this 2.4 is also the same as the 2.4 over here, right? This is also 2.4. So I can take the 95% that's in the middle and still in yellow that wouldn't have been in the green and the orange, right? The middle part. And I can take that 95 and I can add the 2.4. So this would give me 97.4%. And then we can set it up either in a proportion, 97.4 over 100 equals x over 1500. Or 0.974 times the 1500, whichever of those perspectives you prefer. And again, if we need to round, we need to make sure we got a whole number of students. What do you get? Yeah, 1461 students. Okay, there is one piece of information we have not done in this section, so here's what we're going to do. I want you to do the homework for this. I want you to go ahead and start it and all that stuff. I want you to be able to have it completed to ask questions next time, okay? So what I will do is I will talk through its percentiles is the last section, the last page. Any of the questions that are related to percentiles, just push pause on those and wait on those. But anything that's not about percentiles, we'll do questions on next time. You will turn this in then next time without the percentile part, and I won't grade the percentile part, but you'll be able to go back and do the percentile part on your own afterwards, okay? So this will still be turned in, just minus the percentile questions, and you'll know when you see them, they're very clearly stated percentiles, okay?